Video, we're going to talk about Henry's law and how it relates to gas exchange at the respiratory membrane in the lungs. And again, as usual, we want to make sure we understand the law as it's stated generically, as well as its application. And so let's start with the law itself over here, right? And this is sort of a non-traditional way of expressing the law, but I think it best explains what we need to understand for its application to pulmonary function. And what Henry's law basically states is that the concentration of gas, remember the brackets here mean concentration of gas in solution, and actually before I even go on, remember we're moving we're moving oxygen from air into blood, and so it has to go into solution. Carbon dioxide is going to go just the exact opposite direction. Carbon dioxide is coming out of the pulmonary capillary blood and diffusing into the alveolar air, so it will be coming out of solution. And so in either case, the directionality is based upon the direction of the gradient, right? Oxygen higher in the alveolus, and CO2, its higher concentration is higher in the blood, right? And so they're going to be either one will be diffusing down its gradient, but of course that means in opposite directions. So Henry's law helps us explain and understand how gases are sort of moving in and out of solution. So the concentration of gas in solution equals the G just stands for the gas in question here, and so equals the solubility. There are quite a few things that go into what explains that solubility, but think of solubility as the ease with which something moves in or out of a solution, and then it's the partial pressure of that gas. Right? And what we mean by that partial pressure is the pressure of that gas above the solution, right? And so the easy example here, I think, is the way soda is packaged, right? And so if we have our can of soda here, right, we gotta have our lid on it. And when soda is packaged, it's not filled all the way, I'll exaggerate a little bit, but it's not filled all the way to the top. Right? We have a space here that's filled with gas, and it's only carbon dioxide, right? Most sodas, maybe all sodas, are carbonated, right? In other words, carbon dioxide is the gas that's they're pressurized under to carbonate them, right? Makes them fizzy, right? We'll explain that fizzy bit in a second. You can use other gases. There are beers that are nitrogenated instead of carbonated, right? So it doesn't really matter what the gas is. Let's stick with carbon dioxide because that's relevant to our pulmonary function here. Now, remember when we talked about air, the atmospheric air, the concentration of carbon dioxide is really low. It's less than 1 millimeter of mercury, right? And so you can't use air to drive carbon dioxide into solution because there's really not, right? As a percentage, it's a very small fraction of the total. So we use pure carbon dioxide, and we're going to have it in here at about 4 times, well, let me do it this way, at what's called 4 atmospheres, which is the same thing as saying 4 times atmospheric pressure. Units are written as ATM. So in other words, it's not 760 millimeters of mercury of carbon dioxide, it's 4 times that, right? And that actually helps explain, right? When we go ahead and we open this, right? We open it, we get that sort of sound, right? And the gas escapes because the pressure in this space is 4 times the pressure in the atmosphere out here, right? PATM. Okay. Now, right, so that explains the sound it makes when you open a can of soda. But what we're more interested in is the fact that the concentration of gas in our soda here the amount, right, the concentration, the amount per volume, is based upon both its solubility and the partial pressure of that gas. Well, we just said the partial pressure of that gas was really high, right? And that, combined with its solubility, is going to push carbon dioxide over time into the solution, right? And so we end up with carbon dioxide molecules in this solution, and they're going to, right, they'll initially move into the layer at the top, and they'll diffuse, throughout eventually if it sits for long enough, right? And, they're diffusing back out, but again, would they be diffusing out at the same rate they're diffusing in, at least initially? Right, immediately after packaging? Absolutely not, right? Because the concentration in the soda is very, very low, and the concentration out here, right, in this headspace, if you will, is very, very high. Okay, so we're going to get lots of movement into solution, and again, the amount will be based upon the solubility and the magnitude of that pressure. Okay, so when we open the soda, right, and we allow this 4 atmospheres of carbon dioxide to fall, right, this is going to becomes less than 1 millimeter of mercury. Remember, it was 4 times 760, right? Really high pressure. And so all of a sudden we have, right, here's our carbon dioxide out in the air. There's one and there's one, right? And this would be probably way higher than I even have it here in terms of density, right? So all of a sudden, right, here's your one carbon dioxide molecule out here, right? All of a sudden we have this big gradient, right? And our carbon dioxide will move out of solution, right? And that's where the bubbles come from. And so you can think of our blood flowing through pulmonary capillaries here. Here's our inflow end, right? Our arterial flow. And the carbon dioxide is higher here, right? PCO2 is about 45, right? We said this in a previous video. Whereas in the alveolar air, PCO2 is about 40. And so our carbon dioxide, right, is going to move in this direction based upon that gradient. Okay? All right. Now, oxygen, of course, has the opposite gradient, and the PO2 of this pulmonary capillary blood, and it's more variable than the CO2. It's actually in the 20 to 40 range based upon whether you're active or you're exercising, right? If you're at rest or you're exercising, right? The 20 would be lower, and so that would be during exercise when you're removing more oxygen from the blood, and the 40 would be at rest when you're removing less. And again, we'll get to the explanation of that, how we unload more during exercise in another video, right? But let's look at this picture now, right? Let's analyze it, right? We've got our alveolar wall here, right? Remember, that's our squamous cells. We've got our capillary of squamous cells, right? And diffusion is going to occur across that barrier, the respiratory membrane here. That's if I circled the separation here between the alveolar air and the blood, that would be the respiratory membrane. And Fick's law will describe the factors affecting diffusion there, but Henry's law helps us explain the gases moving into or out of solution based upon the partial pressure of the gas above the solution, right? So the partial pressure of the gas at the CO2 is 40, right? The partial pressure of the gas in the blood coming in is 40, and so we have a gradient, right? Much like when we opened our soda over here, right? We had a gradient of carbon dioxide to move back out of the soda. Well, here it's going to move out of the blood and into the alveolar air so we can exhale it. Well, ventilation all day long keeps this PCO2 at 40, and this inflowing blood is always going to have a higher PCO2, so we'll always have carbon dioxide moving into the alveolar air. Okay, now, as the blood moves across the surface of the alveolus, there's this schematic where there's only one capillary running across the surface of this alveolus, not anatomically correct, but for the purposes here, it's going to allow us to sort of assess what's happening to our blood O2 levels, right? Here's our 40 coming in, right? There's our resting value of our blood coming in. It doesn't have zero oxygen in it. It's at a partial pressure of 40 millimeters of mercury. Notice, here's our 100, right? Remember our PO2. Now, I usually round it down, right? So that's this value. I just round that 105 down to 100. And you'll note that at 100, my line's not perfectly straight here. At 100, right, we become fully saturated, right? And so here's the bit, is it takes a little bit of distance for the oxygen. See these darker arrows, right? These darker arrows are indicating, right, our movement, our net movement of oxygen from the alveolar air into the blood. Now, the capillary blood only takes about, let me check this out, only takes 3/4 of a second to pass through the capillary on average, right? So, I mean, there's not much time to sort of get the oxygen into the blood, right? But check it out. You don't even need all that time. Within a third of the distance across the capillary, right? A third of the way across, we got another 2/3, right? Length over here, where really nothing's happening. I mean, the gases are diffusing back and forth, but they've already equilibrated, right? And so it's really only over this first third of the capillary distance that we reach, the gases are having net diffusion, and we reach equilibrium. And so you kind of think, well, we don't even need this other, 2/3 of time and distance, as blood traverses the rest of the capillary. And during rest, that's actually true, right? We've got this sort of buffer where we reach equilibrium, and then there's even more time than we need to reach that equilibrium. Okay, so our blood is going to leave this pulmonary capillary equilibrated with the alveolar air, both the PCO2 and the PO2, right? So the outflowing values would match the values here in the alveolus of 40 and again about 100 for CO2 and O2 respectively. All right. Now, why all this sort of buffer, right? And again, we've gone beyond Henry's law here, but we want to talk a little bit about this exchange that Henry's law helped us explain, this exchange from air to fluid and fluid to air. And what I want to do is basically, that's probably a faster way to do this. I want to show you another scenario here. In this scenario, right, exact same picture we just had, right? Here's our alveolus, the same gases, here's our pulmonary capillary, but now we are exercising, okay? And so you'll notice a couple of things have changed. We're exercising, so our blood is coming now in at a PO2 of 20 instead of 40, right? Again, that means that we unloaded more oxygen at the tissues before we sent it back into the pulmonary circuit. So now it's lower oxygenation. Check this out. Now the blood is traversing the pulmonary capillaries in 1/4 of a second, right? Instead of 3/4 of a second, it's moving much faster. It's moving 3 times faster and traversing the capillary in 1/3 the amount of time. Here's where that buffer comes into play, right? That buffer of when you were at rest, where you were already equilibrated, right? You'll still equilibrate, right? You made it to 100, a PO2 of 100, which again is saturated with oxygen. The pulmonary blood is saturated with oxygen. And you didn't run out of distance before that happened, right? What that means is you are, and you want to be most of the time, perfusion limited. What that means, perfusion means blood flow limited. So think of it this way. The blood was flowing at a third of this rate at rest, right? And it was 100% saturated. Then you doubled that blood flow rate and you were still 100% saturated, meaning you're carrying more oxygen simply because you're carrying, you're moving more blood and saturating more blood, right? In this scenario, when we went to a third of the amount of time, right? So the blood's moving 3 times as fast, yet it's still all becoming saturated. That means you're moving oxygen 3 times as fast, right? The blood's moving 3 times as fast, right? It's becoming completely saturated each time it passes through these capillaries. And so you're carrying 3 times as much oxygen off to your body, right? The tissues that are using oxygen during exercise, right? That's called perfusion limited. You're determining the oxygen carrying based upon the rate at which the blood is flowing. Now, let's give you another scenario here. What would happen in somebody that has a pulmonary disease, and let's say it increases the diffusional distance here. Let's say that, right, remember our diffusional distance is between here and here, right? That's our delta X. Well, in some diseases, fluids accumulate, other things can happen. Mucus can accumulate. Well, not mucus really, but fluids can accumulate. And our delta X could go up. If delta X goes up, think of Fick's law. If distance goes up, what happens to diffusion? It goes down, right? And so the rate at which you would equilibrate down here would slow, right? Because it would take longer for the gases to move, diffuse, if the distance was greater. Right? In which case, our line wouldn't be the one I have here. The line would look like this, right? Or something like this. And remember, when you reach the end of the pulmonary capillaries, that's it, right? There's no more gas movement, right? Same thing up here. Once you've gotten to the end of the pulmonary capillaries, there's no more gas movement because you're not adjacent to the alveolus anymore. So now look what happened, right? Look, you're not at a PO2 of 100 anymore. Now you're at a PO2 of, pick a value here, 75, right? 75. That is not, remember 100 was fully saturated. That was putting as much oxygen into the blood as it can possibly hold. If you're at 75, guess what? You are not fully saturated. You're going away from the lung surface carrying less than optimal amount of blood, in which case you become what is called diffusion limited. So that's diffusion limited gas exchange. Okay? And again, think about that. So now you're limited by diffusion. Could you get more oxygen away if you move the blood even faster? Right? In other words, if you moved it even faster, this would shift right this way in terms of time, right? And it would just, it would still anatomically be at the same place, but what would happen is now you'd get to this point, or this point, or this point, right? In which case you're not perfusion limited anymore, right? You're not limiting your carrying based upon perfusion. You're limiting it based upon, because you're sending the blood flow faster, right? But you're carrying less oxygen, not more oxygen, right? That's not good. That's when you've become diffusion limited, right? That's not ideal. You want to be perfusion limited. Diffusion limited occurs with a lot of respiratory diseases that limit the factors of diffusion, slowing it down. Okay, that's Henry's law and an explanation of our gases moving in and out of solution. Oh, I did want to point out one other thing. Remember in the previous picture, our gradient, so our gradient for O2 is, we'll go with the rest value, right, of 40 and 105. That's a big gradient, right? That's a 65 millimeter mercury difference, right? The CO2 values were, CO2 was 40, and so this was PO2. Oops. So our PO2 in the blood coming in was 40 during rest, and our PCO2 PCO2 in this blood is about 45, right? Remember, our gradient favors moving from the 45 toward the 40. That's a 5 millimeter mercury gradient, right? How could you possibly equilibrate with carbon dioxide with such a small gradient? Remember, diffusion is based upon the size of the concentration gradient, right? Well, Henry's law, concentration of gas in solution is proportional to the solubility of the gas and the partial pressure of that gas, right? And so what we find is that the solubility of carbon dioxide is much greater than it is for oxygen. So it much more readily, and this is an oversimplification, but it much more readily moves in and out of solution than does, in response to a gradient, than does oxygen.